Um, okay, so I just wanted to start off with this slide here to give you some idea of the breadth of areas that one can work in if you're interested in sequential decision making, sequential treatments. And this is all in mobile health. Here, this is with a company that's trying to improve. It's a company that sells its app to other companies, and these companies then give the app to their employees to help the employee improve their wellness. And they ran one of the studies of the type you're going to see to improve engagement in the app. So this is a business-to-business kind of enterprise. This is a bench research study. All the sensors and wearables were designed by engineers. They're all proprietary, and they're trying to understand, will these sensors give us the data to help people quit smoking? Sarah, I think, might be of most interest to this audience. This is, it's called Substance Abuse Research Assistant. And this is solely a data collection tool. These are all kids. They were recruited out of emergency rooms, and they are at high risk of abusive binge drinking. And the idea is every day our scientific team wanted to understand what was their perceptions of their loneliness, their perceptions of their stress. So even though we had sensors, we wanted to know what their own perceptions of their context was. So we had to have self-report. How do you encourage self-report over many days? It's extremely burdensome. And in this study, we explored different reinforcers and different engagement, momentary reinforcers, momentary engagements to keep people answering self-report questions. And then also, the last thing I just want to draw, so this is completely about data collection. This last one study was run by Kaiser, and for their patients that had bariatric surgery. This was not a research project at all. This was done by a health maintenance organization to improve their care for their patients. So you can see sequential decision making goes, at least in the mobile health context, you can see it goes from companies to standard NIH-funded studies like HeartSteps, which is what we'll talk about today, to more bench research studies with different kinds of engineered sensors, to data collection, to how to improve care for your own patients. It goes across all those areas. So we're going to start off with an intro to mobile health, just to get us all on the same page. And I'll often use HeartSteps, which is a physical activity study, to do that. So in HeartSteps, everyone is wearing a tracker. It's a 42-day study. We have a lot of sensors on the phone that we're collecting data from. How busy their calendar looks over the next couple of hours, where they are, location, and so on. And then every evening there was self-report about their perceptions of their stress. One of the questions that really motivated this study was, in which context is it worthwhile for the smartphone to interrupt the person, audibly ping, and attempt to provide that individual a tailored activity suggestion. So with here, context, I know I'm speaking to a group of mainly sociologists. Context is something that's extreme. In this world, it's very dynamic. It's moment to moment. So how does that context impact an intervention or an exposure at that time? The kind of data you see in these settings is on each individual, you see akin to a whole longitudinal stream of data. The O's, I call them observations. The A's are the treatments, could be an activity message like I spoke about in the last slide. And Y is some type of outcome. And you get observation, we call these actions or treatments, response, observations, actions. So I go through, at each time, these are decision points. We're going to talk about that shortly, observations, treatment, and outcome. It turns out when you go to design a mobile app or a trial involving momentary decision making, enormous amount of science goes into these studies. And one of the first areas it comes in is, what are the kinds of times, what are the potential set of times at which you might provide treatment. These are called decision points. And when we started with Heart Steps, we thought to ourselves, well, let's make the decision points every minute. And the reason why we thought every minute was then the user would feel as if a message could come at any time. Right? So it'd be like real time. It'd have this feeling of real time. However, when we had access to a large amount of tracker data on individuals who had regular jobs, and we discovered that the within-person variance in their physical activity there wasn't a lot of variance except around 5 times. And it was related to their job. And these are the 5 times. So think about this, within-person variance. If you have a lot of variance within your own life around a particular time, what does that tell us? That tells us that that's a time at which you have the ability to sometimes be active. Whereas times at which you're stuck in a committee meeting all the time, well, there's no purpose in this interrupting you to provide a treatment. So deciding when these decision times should be is critical. And here we use these 5 times related to one's job. These times differed by individual, of course, because some people have later jobs that start later in the day. Approximately 5 times a day, every 2 to 2.5 hours, these are our decision points. It came from looking at within-person variance and activity. Then at each decision point, you have observations that are accruing in real time. So there's passively collected data. This is from the sensors on the phone as well as the tracker. And then there's actively collected data, any answers to questions that we ask the individual. And I list some of the types of data we have before I mentioned it earlier. As you can well imagine, one of the big games in this world is to try and reduce the amount of actively collected data because it is so very burdensome to people. Nonetheless, I think as we go into the future, we'll always have some self-report just because we want to understand your perception. Treatment. So it turns out the types of treatment that one can provide with a mobile app, it's much larger than I myself thought. There's cognitive interventions. Say, for example, how do I reframe I lapsed to smoking, how do I reframe that so that I continue to try and stay quit? There's motivational types interventions that can be delivered with a phone to try and help me stay on track. There's interventions that connect me with someone else who's went through a similar situation, more social type of intervention. In our case, we're going to have these little activity suggestions that are tailored to your setting. So it's a whole variety of types of interventions that could be provided. There's also engagement strategies, little reinforcers to help you give us answers to our questions. So that's types of treatments, engagement strategies. And then there's whether to provide a treatment at all. That is, should we even at this time interrupt that person in their life in order to either provide a treatment or to ask a question or to reinforce them, right? And what we're going to do, at least at the beginning of this talk, is we're going to focus on this second, whether to provide a treatment at all. And the reason we're doing this is because of the potential iatrogenic effects of interrupting someone in their daily life to attempt to provide treatment. You can expect as a result that the signal is going to be highest between providing something versus not interrupting them at all, as opposed to different types of treatments. So here's an example from Heart Steps. This was in the morning, it was at work. The content of this message is tailored to the weather at that time, whether it's a weekday or weekend, whether you're at work or at home, and the time of day. And you have, this appears on your lock screen, and then you have multiple ways to wipe it away. Swipe it away, and you can swipe it away by pressing thumbs down. You didn't like it. So it's a very unobtrusive way to collect self-report. You can swipe it away by pressing thumbs up. You like the message. Or you can swipe it away by pressing this middle button And if you do that, drop-down menu, you see a drop-down menu, and it allows you to turn off these notifications for a certain number of hours. So this was really nice. In fact, when I trialed this, I would turn it off whenever I had a committee meeting or so on. So the user has control. They're not going to be interrupted if they don't want to be interrupted. So a complication that comes up that's really interesting that people often don't think about in sequential treatments or sequential decision making. Let me just interrupt. I want to just stop. You know, in all across the social sciences, we have sequential decision-making problems. I just want to make sure we're all on the same page. Any kind of welfare program is a sequential decision-making problem for a chronic disorder going in and out of poverty. Any kind of criminal justice type program is a sequential decision-making problem. Mobile health also is a sequential decision-making problem. We're all on the same page on this. Okay, so it turns out that in mobile health in particular, there's some times which it's just completely inappropriate to provide treatment. For example, if the sensors on the phone detect that you might be driving a vehicle, it would be unethical for your phone to interrupt you and possibly cause an accident. So if the sensors detect that you might be driving a vehicle, you cannot get a message, no matter what. And because these messages are all about undertaking new physical activities, if you're currently active right now, we will not interrupt you to suggest that you change and do something different, because it doesn't make any sense. Right, so this is this notion of availability. So in certain contexts, you only have particular treatments that you can provide. And in our case, in this particular simple case, in certain contexts, you cannot provide treatment at all. This availability, it's known before that decision. It's known before you make any attempt to reach out to the individual. It's pre-treatment. That's very different from adherence, right? Adherence is post-treatment. So I was extremely non-adherent when I would hear my phone ping, it would be in my backpack, and I'd just ignore it. That's non-adherence. You discover non-adherence post-decision point, post-treatment. So, okay. Availability is a pre-treatment variable. We're going to only look at treatment effects among those people who are available at that time. It often doesn't even make sense to ask about the treatment effect if they're not available. Again, consideration, every single thing I've gone through here, enormous amount of science needs to go into it. And at this point in mobile health, we're still in the stage where we're still trying to figure out how to use science to even think about these parts of an intervention. So, and this also holds for the proximal outcome. So most of the time, these little messages, cognitive messages, social messages, they're intended to help you at that moment. You may remember them later on and try it out, that's fine, but their greatest impact is expected to be in that moment. And that's particularly the case with these activity messages. So when you think of the outcome, the proximal outcome, it's something really close in time. So here we said step count over 30 minutes following a decision point. Now, you might think, we sat there and we thought, well, how long should this time be? Why should it be 30 minutes? You might think an hour because you have to give people enough time to act on the message, right? But if you wait a whole hour, if you wait very long, people will have time to get out of the current context, the context in which you tailored that message for, and the message is no longer as actionable. If you make it 15 minutes, on the other hand, they may not have time to act on it. So thinking very carefully about the duration of our outcome is critical here. I've been on teams where we've had massive arguments about this type of thing. So our lab looks at, we're focused on sequential decision making in mobile health, and we work on it in 4 different areas, and we're going to focus on the second area, which is related to causal inference. But right now, for example, we have a trial that's going into the field in the next month where we'll have algorithms that learn and personalize the intervention. I can talk about that with people afterwards. So our trials are the data that we're going to be looking at is from what's called a micro-randomized trial. So in Heart Steps, it was a 42-day trial. There were 5 decision points per day related to the person's work schedule. So capital T is 42 times 5, 210. You have observations like we've seen already. You know whether or not the person is available at each of those 5 times. You also know what probability that person was randomized to treatment or not. Now, I wrote this using an equation. It's the probability of A, the indicator of treatment, being 1, given all the data prior to that time and the fact that the individual is available. Often, in Heart Steps, this is just going to be a constant number. But often this is the output of an algorithm. We have other studies right now where this is all the output of an algorithm. But we always know that probability. And then you have your outcome, which I already spoke about earlier. So the data has this type of data. There's N participants, capital T time, decision points. So how might, I just want to go how you might think about analyzing this data. And I want to think about it in a very conceptual way. And that's the reason why I say conceptual is that's the reason why there's these little quotes here. How would I structure my questions when I have this type of data? Well, we already know I'm very interested in, first of all, do these suggestions have any impact on you at all? And do they have a differential impact in certain contexts? So this is the A is 1 if you got a treatment, 0 otherwise. So this coefficient is about the effect of treatment. And then you start looking at context here, moderation. So I want to go through all of this. What do these equations mean conceptually? So the blue part here, what's the gain with the blue part? There's no treatment indicator. AT is not there. This is not part of the science. There's no, if I'm interested in the domain science, I'm not really interested in this part at all. The whole game here is to reduce noise. So often these Z's are pre-treatment measures of the outcome that I'm interested in. So for example, if you're looking at reading tutoring and you have a treatment for reading tutoring, Z would be the pre-treatment reading ability and Y would be the post-treatment reading ability. It's a natural thing. So the whole focus, it's not domain science, it doesn't help us advance our world, it just reduces noise so that we can detect effects, detect moderation. That's the whole purpose of this part.
So you assume away interaction effects of multiple treatments over time.
So right now I'm just focusing on one time point.
There's no compounding effects.
Right now I'm just focusing on that particular time point. So what happens is these coefficients here maybe have been impacted by prior treatment. And you're going to see this when we get to the causal. So you're anticipating. Okay. Often people call these control variables. So we're just focusing on one time point. We're pretending like we have one time point. Its AT can be 1 or 0. It's like a 2-arm study. What's the blue part of the model? That's where the science is. This is what we care about. If you care about the science of helping people in mobile health. So how do I interpret the coefficient of my treatment indicator? Remember, this is 1 if you get a message, an activity message, 0 otherwise. How do I interpret that? Well, it's the effect, marginal over all observed and unobserved variables of providing an activity message on subsequent, in this case, step count. Why do I say it's marginal? It's marginal because I'm not taking into account the time of day. It's marginal because I'm not taking into account the location the individual is at the time they get the message. It's marginal because I'm not taking into account the gender of the individual or their BMI at this time. It's marginal over all kinds of observed variables. But we also have randomization here. It's going to be marginal also over unobserved variables as well. Like I may not know, for example, whether or not people had a big fight with their child in the morning trying to get them to school, and thus they're much less able to be attentive to my message. It's marginal over that. It's causal, because AT is going to be randomized, and we know the randomization probability. It's a causal effect, but it's a contrast. You got the message versus not, on average across time of the day of the week, weather, so on and so forth. It's both marginal and causal. We go now to look at moderation effects, which is on the bottom. Again, this is all conceptual, and I made a real simple moderator. Weather is good, S is 1. Weather is bad, S is 0. Just making it very simple for me to help me explain. So now I have to interpret two regression coefficients. The sum, of course, occurs when the weather is good. So here, again, this sum is my effect when the weather is good of getting a message versus not. It's marginal. It's over the gender of the individual. It's over the time of day. It's marginal over whether or not they're at home or work. It's always marginal. The only thing we're taking into account here is whether the weather is currently good or not. It's still causal, right? So as you can well imagine, the more data I have, the more I can start to look and get closer and closer to the current context, the more specifics of the current context, both the internal context of the individual as well as the external context. I can start to see, is there a treatment difference according to that context? So this is how we think about analyzing data at one point in time. So what was our goal here? Our goal was to develop a method that would give us estimators that are consistent with this meaning of causal yet marginal. Always marginal. It would always be marginal. I can never put all my moderators in. I never have enough data to do that. The issue here, though, is the treatment is time varying. It's not a one-point treatment like did I get pregnant or did I not. It's a time varying treatment. It's something that's occurring day in and day out over 42 days. And my independent variables, my variables that I want to use to control the noise, or I want to look to see if there's moderation, they're not independent, because this is related to what Yushia had said earlier. They could have very well been impacted by prior treatment. Indeed, whether or not I'm available right now for treatment could have been impacted by how many times you treated me before. We want to be able to deal with this. We want to still come up with a causal estimator, but deal with the fact that our independent variables are not independent in a traditional sense. They could be impacted by prior treatment. And the last thing we want to do, and this is common across most clinical trials, randomized trials, is we want to robustly facilitate noise reduction using those controls. We want to make sure that you don't have to know how to model how the controls enter the model. You don't want to have to know exactly how they should enter in order to reduce variance. Okay, so how am I going to tackle this? Well, I'm going to follow the lead of all the people that come before me in causal inference, and I'll precisely state my estimand using the notion of potential outcomes. And that's where you really start to understand exactly what is being estimated here. So now we're in this time-varying treatment setting, right? So at every time we have a binary treatment. A1 can be 1 or 0. So if we go to T time units, time periods, well, there can be T treatments. And these are the realizations of the treatment. So this is just a vector of 1s and 0s. So how many different patterns are there? There's 2 to the T patterns of treatment. For every one of those patterns of treatment, there's an outcome that can occur. So like if you think of me, I get a message versus I don't, this is my step count in the subsequent 30 minutes, and that step count could be impacted by all the messages that I got up to that time. So there's many different proximal outcomes because each one corresponds to the different pattern of treatments I could have gotten up to that time. There's also my indicator. It could be impacted by prior treatment, right? Because if I got a lot of treatment, maybe I'm getting disengaged and I don't even, I've turned off the intervention all the time. I'm no longer available. But notice that my outcome is impacted by the last AT, but my availability is not. That's because availability is pre-treatment, outcome is post-treatment. So how this one has an AT at the end of the vector, but this one only has AT minus 1. And then, of course, we have all the data that's accumulated on me as I've gone through the study up to that time. All of that could be impacted by my treatment. So here's how we want to define our treatment effect at time t. You know it's a causal treatment effect. Here's treated at time t is 1, AT equal 1, minus this is my step count if I got treated at time at time t, minus my step count if I didn't get treated at time t. So that's a difference, that's a causal estimate. So it's a conditional on availability. I have to be available at that time before I'll even look at it. It's conditional on any, now in our case I used weather, so weather is not impacted by my past treatment, but this could be my mood or other variables. It could have been impacted by my prior treatment. So it only concerns the subpopulation of people who are available at this time. Oh, I don't think this matches, but it's conditional on ST. It's conditional on this variable, but it's marginal over any of the information I have that's not in ST. So if I leave out gender, it's marginal over gender, for example. If I leave out time of day, it's marginal over time of day. This is a very weird causal estimate, and you don't really see this in classical causal inference, and I'm going to point out why on the next slide. So it's conditional, we know that. It's marginal because we're not including a lot of variables. We got that, that's standard. But it's the next part that makes it unusual. And that's the fact that it's an excursion. And I want to explain what I mean by that. So how did I get up to time t? I got to time t, I'm a participant in this study, by experiencing a series of treatments prior to that time. That series of treatments can impact my responsivity to the next treatment. So it's an excursion from where I am, so if you think about this in a dynamic way, at each point in time, I got to this point in time under a certain treatment protocol, treatment regime. Now I look into the future and I say, I'm going to now take an excursion from that point, and I'll get treated versus I don't. What will be my step count in future? You can have excursions that go into the future as well. Like I could get treatment and then no more treatment for the next 30 minutes, for the next 3 hours. And no treatment, then no more treatment for the next 3 hours. And you can say, well, what would be the impact? So in other words, at each time I got to this time point under a certain regime, and you ask, looking forward, what's the best? Should I go get treatment now and no more treatment for the next 3 hours? Don't get treatment now and no more treatment for the next 3 hours? Or in this case, it's just, should I get treatment now versus not, and the impact is over the next 30 minutes. But you can think of excursions that go forward in time. Why am I thinking like this? I just want to bring this up. So if you want to have an application on your phone that's going to help you with some chronic problem that you're struggling with, managing your weight, managing an addiction, managing depression, we want that phone to be with you over longer periods of time, right? So we have to constantly allow the phone, that software on the phone has to constantly be checking if certain excursions, one excursion is better than another. And if an excursion is better, one excursion is better than another, looking forward in time, we may move towards that excursion. So you want to continually learn in what settings is this message useful for a person. And the person I am, I know I'm saying a lot, I'm trying to communicate a lot of things. The person I am now is not the person I was 2 weeks ago. And so if I'm in a similar context now, I may be different. It may be that I'm more or less responsive now than I was 2 weeks ago. So the idea of an excursion is to help us to continually learn as we look towards the future. Okay, here's some math. So wait, I'll go back. So if you work in causal inference, you know there's two ways that we always translate potential outcomes to observable data. You either use importance weights, propensity scores, or you use repeated expectations. And that's the two ways I wrote on the next slide. The top way here is the repeated expectations way, and the bottom way, this is the randomization probabilities, is using the randomization probabilities are the propensity weights here. This is using propensity weights. That's the way. It's always one or the other. You can always you get to choose. Okay, so I'm going to use the repeated expectations approach here. So we have randomization, so our potential outcomes can be, our causal estimate can be expressed this way in terms of the real data. So I just want to go through this. This is my mean step count over the next 30 minutes if I got treated, and I was available, of course, given everything that happened to me prior to that time, minus my mean step count in the next 30 minutes. If I don't get treated, I was available in everything that happened in that up to that time. And now I take that contrast and I condition on the particular aspect of the context that I'm interested in. So this ST could very well leave out my gender, or it could leave out whether or not I'm at home at work. ST could only be the weather, for example. So that's what this extra conditioning statement is. I'm only conditioning on an aspect of my context. And what we'll do is we'll model this. Now, if you, depending on how much data one has access to, often these STs are actually predictors of risk. So like ST might be 1 if my prediction of risk over the next day is high, and 0 otherwise. So they're often summaries of my data. I just want us to be aware of that. But here we can think of weather because it's easier for me to explain. So our goal is to conduct inference about this coefficient. And this doesn't have to be linear. If you're totally into machine learning and you have enough data, these can be basis functions. That's not the point here. So what we did was we developed an estimation method. And this estimation method actually follows in the footsteps of people who do factorial experimental design. It doesn't seem that way at first, but it follows in their footsteps. It's a relatively simple method. Actually, at first it was very complex, and then I realized we could make it simpler. And now my behavioral science colleagues, they can do this. They don't need me. It's great. You know, they can do their own analyses. They're quantitative people. They can do it themselves. And it enables unbiased inference for these causal but marginal treatment effects. And better yet, the treatment effect is not biased by how we use controls. And this idea, it's a kind of an intersection of an idea from econometrics and factorial design. You're going to see it next. Okay, I'm going to give you an algorithm here. This is the algorithm. The first thing you do is you make up some probabilities. We're going to call it, let's just think of them in our mind as 1/2. So let's just set this to 1/2. Then you form weights. So this is 1/2. This is 1 minus 1/2. So it's 1/2 in the numerator. Here's your randomization probabilities in the denominator. That's your weights. You center your treatment indicator. This is the same thing as contrast coding in experimental design. And if you've ever had an experimental design class, they always try to get you to use contrast coding, -1, 1, or -1/2, +1/2, because it implies a lot of robustness. And then you minimize what appears to be weighted least squares. So here's the sum over time of my step count in the next 30 minutes. Here's my controls there. My weighted treatment indicator, this is 1/2. And then however I'm going to be modeling my treatment effect. And there's my weight, which you formed before. En is just the average over the data. That's all, it's just weighted least squares. Nothing special. The nice thing about the apparent use of weighted least squares is that it gives you really good intuition, but it can also send you down tracks that are incorrect, and that's what I'm going to talk about right now. So good but incorrect intuition. I see this weighted least squares, I say, oh, I know exactly what I'm doing. I'm just doing regression. I'm doing regression with a contrast coding that is AT minus 1/2 centered treatments, and thus I must be making this assumption that the mean step count over the next 30 minutes, given treatment, given availability, given the controls, has this linear form. That's what I would think. I mean, if you showed me the weighted least squares, this is what I would think. It turns out this is completely fallacious. This is not what is happening here. The only assumption that's being made, well, here I state this more correctly. We're not making this assumption. The only assumption we're making is that our treatment effect has that interaction term. Why am I able to do this? It's because of this, I'm going to go back a slide. It's because of this contrast coding. This part of the design matrix is orthogonal to this part of the design matrix. And so you preserve consistency. And that comes straight out. I've seen it a little bit in econometrics, but I've also seen it in factorial experimental design. Okay, so you get consistency as long as the numerator, this is the numerator of the weights, we were making it 1/2. As long as it depends at most on ST, you get consistency. It's not a big deal. You can derive the standard errors. It's like the sandwich standard error that people use when they use a lot of SAS products. Okay, so what does one gain here? We have, because we're randomizing, we're able to get this causal, this excursion effect. It's marginal. And this method, because of that contrast coding, gives us robustness to a guess at what the step count would be in the next 30 minutes if you're available and given your entire past history. So how does a domain scientist, my colleagues, these are behavioral scientists, they're not social scientists, but they're behavioral scientists, they think to themselves, what variables do I usually control for in these analyses? These are the variables they're going to put in. And you can imagine in heart steps, it'll be the pre-treatment 30-minute step count. So at every time point, we look at the step count in the prior 30 minutes, and we control for that. That's a very near-time proxy for the step count after the 30 minutes. I want to contrast this to, there's this nice literature, this comes out of machine learning and high-dimensional inference, varying coefficient models, partially linear, single index models. These types of models don't have this robustness. You have to get the baseline part of the model correct. But these models were not intended for causal inference. So there is a price here, and that's that because we all know, like if I followed a person over time, don't look at the math. If I just follow a person over time, I know that my step count after each one of those 30 minutes, they've got to be correlated. I mean, really, it's got to be correlated, right? And so you would think that I should use the within-person correlation in step count. Somehow I should use that to increase this, to reduce the noise. I should model the within-person correlation step count to reduce noise. I mean, that would be you can't do that here. You mess up the causal inference. This is really interesting, I think, is that by trying to take advantage of the fact that I know there's got to be within-person correlation in step count across time, I will mess up the causal inference. And I'm going to just explain to you how this happens. This is the math. Okay, so the math is, here's my equation. This is the first derivative of the least squares. So I'm taking the first derivative, and here I have off-diagonal elements. I'm using a correlation matrix. ZU is my control at another time point U. Let's make U equal t plus 1. Okay? Suppose my control at time t plus 1 was my step count at time t plus 1, right? Because that's pre-t plus 2 treatment. So this could easily be yt plus 1. If this is yt plus 1, there is no way this is going to be 0. Because here you have yt plus 1 minus, even if you assume this is its conditional mean, times yt plus 1. I'm going to get a variance term. That ruins this messes up the causal inference. So you cannot have, these have to all be 0. That's the point I'm making. Okay. I wanted to talk to you about the numerators. They're all 1/2, remember? We made them 1/2. The whole purpose of the numerator is to allow you to deal with the fact that you might have parameterized the effect of the context on the treatment in a realm. And you want to have an interpretable estimator of the moderating effect of the context on the treatment. And here's an example. Suppose ST is just 1, it's just an intercept, and I make a constant probability like 1/2. This is 1/2. What am I estimating when I go through this entire procedure? Remember, IT is 1 if you're available, 0 or not, so this is the fraction of time I'm available at time t. Beta t is my effect at time t. That's all it is my effect at that time, my average marginal effect at that time. So what am I estimating? I'm estimating a weighted average, weighted by my availability of the treatment effect at each time. So it's something, like I can explain this to my behavioral science collaborators, and they know, they get it. They're okay with this. They know, so that if my model's wrong, I'm still estimating something, they know it, and they know what it is. Okay, I want to show how this worked with heart steps. So if you don't like math, you can wake up now. Because this is actually really interesting. There's a lot of interesting behavioral science that came up in this study. Okay, so here's a schematic of the trial. This is a factorial design. There's 2 factors, both of which change with time. One factor is that so you can always tell how many factors there are by the green R's. And here's one factor, here's the other. This is the one we've been talking about. You get your observations, you say, is the person driving? If not, you can continue on. Are they walking right now? If not, you can continue on, and then you can randomize them. And you randomize them 5 times a day, if the answer has always been no and they're available. That's our tailored activity messages, tailored to this aspect of context. The other factor is every evening they could be randomized to plan how they're going to be active tomorrow. Notice the difference in time scale. One exposure or treatment is 5 times a day. The other is every day. We have other studies where there's one that's every week, or ones that they're just baseline. And let's think about the outcome here. The science, you can start to see how the science really becomes important, the behavioral science. The outcome for these that are 5 times a day, this is the 30-minute step count after a decision point. The outcome at the evening, because you're planning all of tomorrow's activity, is the total step count tomorrow. So every factor in this factorial design has its own sort of time scale, its own outcome. And what is the purpose of a study of this type? It's to build a mobile health intervention. That's what factorial studies are for, to build an intervention. So this is 37 participants. We actually sized this study to address this question, the first question. It was sized for this purpose. We have a sample size calculator. We decided on a randomization probability of 0.6 because we wanted around 3 messages per day, and there were only 5 opportunities. So 3 divided by 5. So provide a suggestion, a tailored activity suggestion with probability 0.6, or don't bother the person at all with probability 0.4. This occurs 5 times a day, assuming they're available, over the 42 days. So there's 210 opportunities, potential opportunities. Here's our conceptual model. Again, we're putting quotes here because this is not a model for the mean of y given z and x. That's not what it is. And I'm just going to focus on this part. But let's just go. Why is the step count over the 30 minutes, subsequent 30 minutes? It's log transformed. This is a highly skewed variable, and people traditionally transform it with a log so that you get better approximations with a normal distribution. Z is the step count, the log transformed step count in the 30 minutes prior to the decision point. So notice the dynamic nature of these types of analyses. The pre-treatment variables are dynamic. The outcomes are dynamic. Everything is evolving through time. A is an indicator of suggestion or not. Oh, now the second analysis, we pre-specified our primary analysis. This was the overall effect of giving a message versus not. This is an indicator of day in study, DT. It's 0 the first day of the study, and on the 42nd day of the study, it's 41, okay? Why do we have this right here? We were very concerned about burden due to us interrupting people and habituation. We know from psychology that if you provide a series of stimuli, people start to habituate to the stimuli. And so we were really concerned. So our primary hypothesis in this study was, is there an effect at all? And does it dissipate? So here are the outcomes of the analysis. And everything's on the log scale, so I have to interpret it for you. Okay, so this is the overall effect. I give you a message versus a not, marginal across the time of the day, your gender, and so on, day of the week, whether you're at home or work, and it's 0.13, and that's about a 15% increase in step count. These are very sedentary people. Around these 5 times, they would get around 250 steps in a 30-minute window. So it's around 33 steps more than 250. Now let's look at this next one. So this is okay. I mean, it's 0.06. We know the p-value problems with publishing, but it's still pretty good. The confidence interval looks good. Now we go to our next analysis. Remember, DT is 0 on day 1, and then it increments by 1 every day. So the interpretation of this coefficient is the effect early in the study, and then the interpretation of this coefficient is how does the effect vary with time. These are coarse things, right? Coarse over time. So 0.51, it's highly significant. This is a approximate 65% increase in step count. The usual 250 steps going up to 170 plus 250. So it's a massive effect early in the study. And this was a really big deal. Then you look at this and you see it's negative, and you know, it was exactly what we were worried about, habituation. And you think, well, it's so small, maybe it doesn't count. Maybe it's a 6-week study, it shouldn't really accumulate. But remember, it's 5 times a day. It's accumulating at times of 5 times a day. By day, halfway through the study, 3 weeks in, the effect is completely gone. Very interesting. So what's happening in the next iteration of this study? Because we were funded to do 3 studies, all with the goal of developing this app. In this next iteration, we have an algorithm which is tracking your responsivity to the message. If you start to reduce in your responsivity, it decreases the chance you will get a message in the hopes that you'd start to dishabituate. And then every now and then you still get a message, so that we detect whether or not you've become dishabituated, and we can start bringing it back in again. We'll see if the algorithm works, right? I mean, we don't know. People liked this particular message because it was so actionable. Anyway, very interesting outcome here. Okay, so now I want to go on. There were 2 types of activity messages in this study. And this had a lot. I can't tell you how much domain science goes in. I've said this over and over again, but this is continuing on. So in physical activity, it's thought that if we can just get you to stand up, then you will start to move. And there had been a lot of studies, like 2-arm trials, black box kind of things, where they had these anti-sedentary messages. And the goal was just to get you to stand up. And they saw that the arm that had the anti-sedentary message did better than the control. So the idea here was, look, if we just give you an anti-sedentary message, these are great messages. They would say, like, why don't you stand up and roll, make your toes go around in your shoes, or roll your arms, you know, it's great. You didn't do a thing, you just stand up, do that, and then you sit back down. Right. So that was one of the activity messages was of that type, and the other was more onerous. It took like 3 minutes. Why don't you walk until you see that squirrel kind of thing. So this is the more onerous message. This is the one everyone loved. We did a lot of exit interviews. People loved this message. Right. And there was this accidental evidence from the literature that said the anti-sedentary messages should work because you'd stand up and move. Right. Okay. So here we have two indicators, right? So we have two treatment effects, two average treatment effects. AT is 1 if you get that more onerous 3-minute suggestion, 0 otherwise. A2 is 1 if you get the anti-sedentary message, 0 otherwise. I think the p-value here was like 0.85 or something. This is the one for the more onerous message. So essentially all of our, okay, 0.21, that's about a 25% increase in your step count. I'll tell you on the next slide when we interacted it with day and study to test for the habituation type. But this, so it was the more onerous message, the one that meant you had to take a 3-minute walk or so, that actually impacted. This is really interesting because in this literature, it was thought that if you could get someone to stand up, they would start to move. And now we have this momentary evidence that that's potentially fallacious. We have to replicate this with a bigger study because we didn't size for equivalence. We sized to detect effect, right? Now we did interact that with time and study, and so here's the conclusion. The effect was there. The data indicates there's a causal effect of the activity suggestion on step count in the succeeding 30 minutes. Unfortunately, it's primarily due to these 3-minute walking suggestions. Unfortunately, the effect deteriorates with time and is essentially gone 3 weeks in. But early in the study, the effect was increased your 30-minute step count by around 270 steps. Remember, the usual is 250. So it just about doubled the step count early in the study, if it was a 3-minute suggestion versus nothing. But by 3 weeks in, over. Again, all of this impacted our next study. It turns out the other factor, I won't tell you about the analyses for the other factor, it had a more onerous version and a less onerous version, and then there was no treatment. Again, the entire impact was due to the more onerous version. We had a more onerous version of planning tomorrow's physical activity. Very interesting from a behavioral science point of view, because this really means that going forward we have to have a lot more engagement and support so that people can undertake that more onerous suggestion. So a lot of people in mobile health who don't have this randomization through time, they want to use multi-level models because, of course, you want to use multi-level models because multi-level models use that within-person correlation over time, and they allow me to predict individual level effects. I mean, of course I want to use multi-level models mess up the causal inference here. I think this is really interesting. So multi-level here is, I'm using the word random effects. I find this really interesting because if you go to the random effects literature, you'll see that we as data scientists have used one hammer to solve 2 problems. And now we're not going to be able to do that anymore. And let me just be clear about this. Our one hammer is the random effects model. The 2 problems are, if I'm a statistician, I want to decrease my noise, so I'm going to model the within-person covariance over time to get better power to detect an effect. I'm a statistician. That's one reason to use a random effects model. Now I'm a behavioral scientist. I want to predict individual level effects. I want to use random effects to predict individual level effects. Now we realize that that one hammer of the random effects model cannot do both of those things. Very, very interesting here. And I'd never thought about that so clearly, that we were running around with our one hammer trying to achieve 2 goals. A lot of the models that people want to use don't mess up the causal inference, and it's mainly because they weren't developed for it. And here's big challenge: how do we start using random effects? Our goal, when we do random effects, our goal is not going to be the statistician's goal. It's going to be predicting person-specific effects. That's what we want to do. We have some work on this now already. This is my last slide. I have these types of studies. This is, it's very similar to some of the stuff a lot of you guys do in your data collection enterprises. This is big science, right? You need a lot of experts. So here, there are computer scientists, people who work on how the phone looks to you and the way in which the phone presents information to you, how that impacts you. That's human-computer interaction. Behavioral scientists, statisticians, app developers, and so on. Everyone has to come together to put something like this in. And the different sciences have to work in a cohesive way. So thanks. I just want to show you, this is Sarah. See Sarah? If you answer our questions, you can level up to the ocean. This person's still in the aquarium. Anyway, that's it. Thank you.